Well, here's part 2 of tube theory. In this part we're going to talk a little bit about 3 different tubes: the triode, the tetrode, and the pentode. The tetrode you won't see too often anymore. They were short-lived, and I'll get into reasons why. But let's look at the triode first and talk about some pros and cons of the triode. One of its biggest benefits of the triode tube is low distortion when it's using it as an amplifier, whether it's a power amplifier or voltage amplifier. And I'll get into the differences between those two in a later video. But it does have a lot less distortion as compared to the tetrode or the pentode as an amplifier. And that's really one of its big advantages. Some of the somewhat disadvantages, I'll talk about 2 minor ones which kind of go in hand. One is the mu on a triode is relatively low. Compared to these other 2 tubes, it is fairly low. They come in roughly 3 different varieties: low mu, medium mu, and high mu. Well, high mu tubes get up around topping out 100 or just a little over 100 for mu. Now, the other thing about them that goes hand in hand into that, when you deal with power tubes, you talk about power sensitivity when you're dealing with power amplifiers. And there's a nice formula for it and stuff, but the basic means of it is it's a way of looking at a tube and kind of comparing tubes and stuff in how well they amplify a signal. Amplify current, basically, because that's what a power amplifier is. Basically what we're looking at is when I put an input voltage into here, I'll get a certain level of output. Well, different tubes may have different outputs for the same input. Well, a high sensitivity tube, one that's really sensitive, will have a much smaller input to get the same output as opposed to a tube with low sensitivity. So basically a high sensitive tube, power sensitive tube, I can really reduce down and not have to have as much input and still get a decent power output. And that goes hand in hand really with the amplification factor mu. Now, one of the big problems with a triode comes from what this green is. These are internal capacitance in the tube. Now, all tubes have it. You know, basically all a capacitor is, by definition, really is 2 plates, parallel plates that are separated electrically by an insulator of some sort. It can be air, it can be mica, some sort of ceramics, paper, whatever. Well, in this case it's vacuum. But each electrode is acting like a plate of a capacitor. So there is a certain amount of capacitance. Now, the first one here is grid to cathode capacitance at 4.2 picofarads. Not important. I put it on here and I tell you it's not important. The only time it's important is really ultra high frequencies. You know, I don't know, 200-300 megahertz and on above is when this starts becoming a problem. Same way with this one. At 5 picofarads, it's between the plate and the cathode. This one, ultra high frequencies, is the only problem area for it. Anything lower than that it don't give any problems. The one that we want to talk about is grid to plate at 3.8 picofarads is a problem. Now, at low frequencies, broadcast band frequencies, you know, the AM radio band, it didn't wield its ugly head. But by 1930, people were wanting to listen to shortwave. You know, it started becoming popular. Well, shortwave, you know, you're into much higher frequencies than your AM broadcast band. You know, you're talking at least going from the AM broadcast band on up. And once you start getting up around 3 and 4 megahertz and on up, this starts becoming a problem. It acts like a leakage in the tube. And depending on how high the frequency gets, it can even almost be like a dead short in the tube, which effectively nulls the amplification. And as it is, even at the lower frequencies, it's one of the primary reasons why the mu is lower on these tubes. Well, there are ways externally to fix or alleviate internal capacitance in a tube. I mean, you can shield them, you can do things like that, and that's some of the simplest ways. You can also add filtering circuitry, positive and negative feedback circuitry, all kinds of different ways of dealing with capacitors. The only problem with that is that costs money. I mean, you got time and materials in that to do that. So manufacturers of radios, you know, demanded something be done, so I left it up to tube manufacturers, and lo and behold, we have the Tetrode. It was born. Now, just like the Triode, except it has an extra grid. This one right here, called the screen grid. Called the screen grid because it's basically screening the control grid, which is what this is, from the plate as far as capacitance is concerned. And if you happen to notice that, and these are, what that wiggly line means is approximate. These vary from tube to tube and everything, but it's considerably less. 0.0007 picofarad is kind of an average value as opposed to 3.8. Considerably less capacitance. Now, how that's done is what we do with the screen grid. And what we're doing with it, we're applying a positive voltage to it. Now, it'll be a little less than the plate as a general rule. If you got 100 volts in the plate, you might have your screen grid running like 80 or 90 volts or even a little less than that. But it becomes a positive shield between the grid and the cathode as far as the capacitance is concerned, breaking it up. Now, yes, there is capacitance between these two, but you've got to remember what we're doing with the tube. The control grid is our input. This is where our signal comes in. The plate is our output, not the screen grid. So, yes, it gets a signal on it. Yes, it has current flow on it and all that, but we're not picking the signal off of it. We're picking it off the plate. And that's where this thing's going to give us problems, is with our signal. So as far as our signal is concerned, it's only looking at these two. It can care less about this one. So it's okay that there is capacitance there because it's not going to affect us. Now, one of the other advantages by reducing this and a few other dynamics that actually happens in the tube by placement of a screen grid, the mu went way up. Remember I said on the Triode we're looking at a high mu tube upwards around 100, not much above that. These can easily hit 600 or even a little above. So quite a bit higher mu, more than 6 times the value of a high mu Triode, which also means they're more power sensitive. So as a power amplifier, it would take a lot less voltage to have the same output as it would for the Triode, which makes designing a circuit a lot easier, and the tube picking the tubes right and everything. Now, that's probably pretty much where it ends, though. The Tetrode had its own little problems. Because this is here and it's positive, we had a problem that showed its ugly head. The electrons, when they decide to leave here, they start going through the tube. Well, they get past the grid. Say the grid is running not real negative, you know, they start accelerating past the grid. First thing they encounter is this positive area right here. Now remember, this is a grid. It's another just coil of wire, so it's not like a big major flat plate. They can easily pass it, and most do. There is some that bombard them wires, get stuck to it, and we have some screen grid current. But more than 90% of them make it pass. But as they make it pass, they continue to accelerate. The plate is a higher voltage, so it even draws them even more. Between the two, we've already increased their speed tremendously as opposed to a triode. What that tends to do is when you get high velocity electrons hitting a plate, if they're moving fast enough, they will actually knock electrons loose from the plate and bounce them right off of there. Well, the distance between here is relatively small, so when they get bounced off, they can bounce off far enough that then they get picked up by the screen grid, depending on the plate voltage. And this is known as secondary emission. Primary emission is the emission from the cathode. Secondary emission is emission from virtually any other electrode in the tube, but primarily in this case the plate. So we start getting an emission from the plate going back to our screen grid. Wrong direction, reduces amplification. Well, it can get really bad at low plate voltages. Now, this here is what they call a plate characteristic, average plate characteristics. Okay, it compares the milliamperes on this side with the plate volts. These lines represent the current, and they also represent the current at certain settings of grid voltage as it crosses. But your current will actually follow kind of parallel to these, but it never goes negative. We never have a negative current. And of course the thing with the triode is they're fairly steep angled. Well, here's plate characteristics for a tetrode. It's actually a 24A, and it's actually an early 24A. The biggest thing, two things, is when you start multi-gridding a tube, your plate current starts leveling out. It doesn't have as much effect on it from the plate voltage anymore. That increases amplification as well. But on the tetrode here, the big thing is this area right here. This little area says values unstable. The voltage here is approximately, around 90 to 100 volts. Excuse me. Anything less than that, these curves start going nuts. This curve here is representing IC2, which means the grid 2 or screen grid currents. This one here represents IB, which is plate current plus screen grid current. And then this one here is representing IB, or plate current. If you notice at around 50 volts, here is my zero line. It goes up early on and then drops down all the way down here. Here's negative current. The current has reversed in the plate at around 50 volts on the plate. It is actually acting as a cathode instead of an anode. So we're getting a flow of electrons total opposite direction they're supposed to. And where are they going? Well, the curves show. Screen grid current way elevated. So they're going from the plate to the screen. Now as we increase the voltage on the plate, eventually it goes across the zero line and starts increasing at the same time. The other current on the screen starts reducing until we hit about this line. Well, that presents a problem. And the problem is, at this point, is when these tubes are introduced. back in the very early 30s, where a lot of radios were battery operated because the entire rural areas hadn't had even electricity yet. Has never been introduced to electricity. So most battery sets run either on 67.5 volt plate voltage or 90 volts plate voltage. Well, 90 volts is the least I can go. I go anything less than that, I get unstable. And the problem is when this thing's acting as a voltage amplifier, the plate will drop below that at times on the swing on the AC signal. I got a problem. Now you can hook these up to AC transformer, increase the, have a secondary step up transformer, get 200-300 volts. That wouldn't be a problem. Batteries, a lot more difficult. So we had to do something, and again we turned to the tube manufacturers, and comes in the pentode. Now here's a pentode. Again, very low capacitance between the control grid and the plate. It's a little bit higher than the Tetra, but not a lot. There is like I said, again, this is a rough, but there are some pentodes that actually have a little bit higher capacitance than a Tetra, but it's still well below Triode and perfectly fine. The low red dotted line is just to show you that some pentode tubes are actually interconnected. From this grid, the new grid that we've added to the cathode. Some tubes, it's not connected here and actually has its own pin. Now, what this tube, or what this grid does, is it counteracts this. And then by doing so, it's called the suppressor grid. It suppresses secondary emission. And the way it does it is by hooking it to a negative. Either ground, cathode, or something. Now, like I say, a lot of them are actually interconnected. There's no tube pin here, but there are some that does have one, so I wanted to show it. Now, the way it does that is just because the fact it is negative. Again, the electrons are moving faster and faster as they go through, and when they get up here, again, it's another screen, it's another grid, coil wire, and they make it pass without any problems, but it does slow them down a little bit. The ones that get fairly close will get really slowed down, where when they get to the plate, everything's perfectly fine. The ones that's out in the middle between the wires are still going pretty fast. So what? They knock off some electrons. Well, what happens now? Those electrons come out in this way. They can't get here. In fact, they don't even sense the screen grid. They see this negative, so they are repelled back to the plate, and that's where they head. And what that gives us, this kind of plate characteristics. No zero. Nothing below zero. In fact, no unstable areas. In fact, we can run way less. Here's 100 volts. We can go way, way down here before we start getting in what they call the knee or the bend of the curve. So, extremely well flat curves, go very low voltage, and they work really good. Now the nice thing about them is the current is even flatter, much flatter than this current, which does have a little bit of an angle, you can see here. That means mu is probably much higher. Well, it is. A decent average for these, 1600 to 2000 on the mu. So they are quite powerful amplifiers as far as amplification goes, which means that they're more sensitive as sensitive power amplifiers, and you can get by with a very small signal to an output signal. Now the only problem with both these tubes, this one not as much as this one can be, is harmonics. They can be pretty bad with harmonics. They're a lot higher percentage-wise than harmonics. These average 5% or less. These 10, 12%, which can be disturbing to the ear. So you have to deal with that when you design an amplifier and work with that problem, and we'll get into that. As far as the rest of the constants, this video is starting to get a little long. It's going to take me quite a while to upload it. So I'll probably end it here, and we'll talk about, well, I'll tell you what, I'll go ahead and run through them real quick. I was hoping this would go faster, but the other two constants, plate resistance and transconductance. The plate resistance on these guys are quite a bit higher than the triode, but at the same token the transconductance is less. Remember from before that mu equals transconductance times the plate resistance. Now these tubes are not much different than the triode, although their mu's can change just a slight bit, but they stay fairly stable, just like the triode under normal operating conditions. So if it got real high mu, then something somewhere has to shift. And where that shift is due to the extra grids and everything, it actually increased the plate resistance, the transconductance went down. So these fairly low transconductance, these plate resistances can be quite high. These can be well in pinto tubes, well into megohms, 1 or 2 megohms of plate resistance, where a triode is more few thousand ohms. So but that goes into with the power amplifier situation. That means that this impedance here is much higher, and that allows it to be a more effective power amplifier as far as power goes, and we'll get into that, talking about the difference between voltage amplifiers and power amplifiers. So anyway, now I think I will end this, and the next time we'll talk about the different types: Class A, B, C, AB1, AB2 amplifiers and operating points. So until next time, thank you for watching.